Over the next decade, millions of first-generation electric vehicle batteries will reach the end of their lifespans, creating a mountainous wave of electronic waste. Locked inside these spent cells are millions of tons of strategic critical minerals, specifically lithium, nickel, and cobalt. The extraction of these metals from decommissioned hardware rather than geological deposits is an industrial priority known as urban mining. These batteries function as highly engineered, electrochemically active devices containing volatile organic solvents. Because these devices remain volatile chemical systems even when discharged, we cannot safely or efficiently recycle them using the brute force physical methods of the 20th century. Historically, the recycling industry relied heavily on pyrometallurgy. This process uses high-temperature smelting furnaces, operating at up to 1600 degrees Celsius, to melt scrap into mixed metallic alloys. Applying this extreme heat to modern lithium-ion batteries results in the catastrophic incineration of the battery's graphite anode and its organic liquid electrolytes. This chart compares recycling recovery profiles. Under pyrometallurgy, the critical element lithium is permanently trapped in waste slag. The modern alternative, hydrometallurgy, utilizes low-temperature aqueous chemistry to achieve high mineral recovery while drastically reducing energy consumption and emissions. To understand how this works, we must trace the physical and chemical journey of a single spent battery down to its atomic base. Achieving a closed-loop supply chain strictly requires mastering the staggering complexities of liquid chemistry. The recycling process begins with mechanical comminution, which involves physically shredding the battery to access the active materials inside. This stage presents a severe industrial danger. A spent battery often retains residual electrical energy and houses highly flammable organic liquid electrolytes. If a steel blade breaches the cell in ambient air, the separator is crushed. This forces the positive and negative layers together, causing an immediate short circuit. This triggers thermal runaway, an exothermic chain reaction where internal temperatures rapidly exceed 1000 degrees Celsius. At these temperatures, the fluorinated electrolyte salts structurally decompose and react with ambient moisture. This specific reaction generates hydrogen fluoride, or HF gas, an acute systemic poison that forms corrosive hydrofluoric acid upon contact with human lungs or eyes. Traditional fire suppression systems are virtually useless here because the degrading metal oxide cathode generates its own oxygen to continuously feed the fire from the inside out. Safely accessing the critical minerals requires an engineering solution that entirely prevents the physics of thermal runaway from initiating in the first place. The industry's highly scalable answer to this threat is submerged comminution, commonly known as wet shredding. In this process, the violent mechanical action of heavy steel shredder blades tearing the battery casings apart happens completely submerged underwater. The liquid bath acts as a massive thermal sink. It instantly absorbs the immense frictional heat and quenches any localized sparking before the electrolyte has a chance to ignite. The water also provides a critical chemical passivation benefit. Any highly reactive elemental lithium is safely oxidized by the surrounding liquid into a stable, less reactive state. After the floating plastics and shredded steel casings are filtered out, the remaining output is a fine, heterogeneous dark powder known as black mass. Black mass serves as the essential physical bridge between electronic waste management and advanced chemical refining. It stabilizes the volatile battery into a safe, usable chemical feedstock. Black mass is highly valuable, but is heavily contaminated with graphite, polymeric binders, and structural impurities. Extracting the transition metal oxides requires precise chemical separation. This marks the first stage of the hydrometallurgical circuit, reductive acid leaching. Recyclers submerge the black mass in highly concentrated inorganic acids, primarily sulfuric acid, combined with hydrogen peroxide. At the molecular level, high concentrations of hydrogen protons from the acid aggressively bombard the crystalline lattice of the solid cathode material. This forces the metal atoms to detach from their physical bonds and dissolve into the fluid. This creates the pregnant leach solution, or PLS. The PLS is a highly acidic, aqueous liquid saturated with dissolved lithium, nickel, cobalt, and manganese. Initial structural impurities, like solid graphite, iron, and aluminum, are subsequently removed through mechanical filtration and basic hydrolytic pH adjustments. While acid leaching successfully liberates the metals from their solid state, we are left with a chaotic liquid mixture. To be useful, these elements must now be painstakingly separated, atom by atom. To be viable for new battery manufacturing, the dissolved metals in the pregnant leach solution must be individually isolated to a strict purity standard exceeding 99.5%. This is achieved through solvent extraction, a highly sophisticated chemical process that relies heavily on liquid-liquid phase transfer to successfully separate the target metals. Recyclers introduce highly specialized organic extractants, specifically dialkyl phosphinic halides like Cyanex 272, into the aqueous PLS. These organic solvents exploit strict thermodynamic complexation preferences, engineered to bind to exactly one type of metal ion. For example, the extractant binds exclusively to cobalt ions, pulling them into the organic phase, leaving nickel ions trapped in the aqueous layer below. This requires a strict linear architectural sequence. You must continuously extract manganese, then cobalt, then nickel, to prevent downstream poisoning of the highly sensitive organic extractants. Finally, the highly soluble lithium is isolated terminally through advanced bicarbonation, precipitating out of the solution as a solid white salt. This sequential thermodynamic sorting is the only known scalable method capable of transitioning a toxic waste slurry back into individual molecularly pure elements. The final outputs of the hydrometallurgical facility are highly purified individualized precursor salts, such as nickel sulfate, cobalt sulfate, and lithium carbonate. Empirical testing consistently demonstrates that these recycled metal salts match and often exceed the morphological stability and electrochemical performance of virgin mined materials. The true advantage of this process reveals itself in the economics. We can directly evaluate the all-in processing costs of hydrometallurgy against the immense expenditures required for primary hard rock mining and brine evaporation. This chart compares processing costs per metric ton. There is a stark contrast between the hydrometallurgical recovery of black mass, which costs between $1,500 and $1,800, and the massive $6,000 to $9,000 cost floor of hard rock lithium mining. This data illustrates a stark economic reality. Recyclers are no longer spending decades extracting trace elements from complex geological ores. They are processing high-concentration, perfect mines. The intrinsic concentration of critical minerals within black mass is exponentially higher than the highest-grade natural ores on Earth, resetting the baseline economics of the global energy transition. Through a highly orchestrated sequence of submerged mechanical neutralization, acidic dissolution, and solvent extraction, we rescue these critical elements from total destruction. By mastering this low-temperature aqueous chemistry, the industry bypasses the massive carbon footprint of traditional smelting and drastically reduces our reliance on vulnerable foreign mining supply chains. A sustainable, electrified future relies on the chemical mastery required to return every gram of recovered metal to the production loop.